terrific.
So, all right,
and
good.
it's Chip Shearer from the University of New Mexico, and it's terrific to be here. Thank you. Very recently, Lisa Gaddis provided a map that was a compilation of pyroclastic deposits on the surface of the moon that's totaled perhaps well over 100. And the remnants of some of these pyroclastic deposits do occur in every Apollo sample or from every Apollo site and every Lunar site. But perhaps the best sample of these pyroclastic deposits are represented by the Shorty Crater deposit at Station 4 in the Taurus Littoral Valley, shown on the images down at the bottom here. And this to the right represents a core of 74001 and 74002. Again, this is a double drive tube. There's been substantial work done on this already, but the last preliminary examination and analysis of the complete stratigraphy was done in the late 70s. And what we're attempting to do is take a better document better the stratigraphy using a variety of thin sections and XCT imaging of the remnants from that core. In addition, we are doing bulk sample analysis of a wide range of stable isotopes, both from the bulk rock and from the coatings on some of the individual of some of the beads. And therefore we're utilizing with other people haven't done is really place a lot of the stable isotope data within a stratigraphic geological context. Just this illustrates some of the data that we've generated with regards to one of the thin sections, illustrating some of the optical data and imaging we produced, BSE imaging from electron microprobe. We did a bunch of magnesium X-ray maps, and of course, as you see to the right, X-ray computer tomography, looking at these in great detail for a three-dimensional examination rather than just a two-dimensional examination. What you'll note here is particularly, it's really well shown in the magnesium X-ray map, are these little bright yellow spots on that map. And these are individual olivine crystals that occur within this stratigraphy. And that's really going to be the focus of this talk rather than everything else that we've done and we are doing. These are kind of rather unique, as you can see to the left. These are fairly large olivines on the order of several hundred microns across and in length. They can occur, they can have iron, nickel, cobalt, metal in them. There are melt inclusions associated with them. They're fairly magnesium rich. And the melt inclusions have been used by Alberto Saul and others to really take a look at the pre-eruptive volatile concentration of the magmas that were erupted in these pyroclastic flows to better understand what was the magmatic volatile content and isotopic content in some cases with regards to hydrogen. And these are dramatically different than some of the olivine that you'll see in actually the black volcanic beads, and that's to the right where the olivine is smaller. It looks like it crystallized prior to following eruption and fragmentation during the eruption. And I think what we can do is from some of the olivines, we can extract a wide range of information from these olivines, particularly if we place them within the context of the stratigraphy that's represented by in this pyroclastic deposit using a new set or different set of tools. First, these olivines have a wide range of morphologies as shown here. They can be fairly euhedral in nature. However, they do appear to, at some places within the flow, tend to be appear to have this reabsorbed texture, as you see in B, C, and D. And in E, you have almost a skeletal olivine of some sort. Again, all representing olivines that were in the magma prior to eruption and fragmentation. And we have some questions. Again, we haven't answered all these, or actually none of them yet. How common are these different morphologies? How are they distributed in the stratigraphy? And how are the iron-nickel droplet distributed within these different morphologies and throughout the stratigraphy? This just illustrates some of the zoning or lack of zoning that you see in these olivines. As you can see, these are a variety of X-ray maps, and really the only kind of zoning that you potentially see is perhaps a little bit in phosphorus. You don't commonly see the cryptic phosphorus zoning that you commonly see in Martian basalts and other lunar basalts. A little bit with regards to titanium, but again, differences of 0.1% TiO2 versus 0.3. And then the nickel abundances change a little bit as one moves into the interior. But again, these nickel abundances are far less abundant than one normally sees in many of the crystalline Mare basalts. I did the old school method of I went through the whole set of thin sections and did standard point counting methods to really get a better understanding of the abundance of these olivines within this column. And you can kind of see it here, where near the base of the pyroclastic deposit, which corresponds to the decrease in the famous orange glass that's commonly more abundant in the upper part of the stratigraphy, and the black beads are more common in the lower part. So we have the black beads, which represent not a rapid cooling rate, but a slow cooling rate in the fire fountaining, being associated with, on the surfaces, higher abundances of surface volatiles. And also, generally, we seem to have these pre-fragmental olivines occurring in the lower part of the core.
3 minutes.
Yeah. And we are training, we're doing some machine training to better understand the non-point counting method by looking at volumes, and we have an undergraduate essentially doing that. Another approach that we can utilize is, again, looking at the XCT imaging and getting a three-dimensional aspect of the variation in these particular olivines. The machine learning is shown in the middle column, where conveniently these olivine compositions contrast with everything else. And Scott Eckley from Johnson Space Center just showed an example here where he did a modal abundance of these olivines within the whole three-dimensional XCT image of the core, and comes up with a number of 0.19%. My point counting method gives us in 2 dimensions about 0.23. What's also quite interesting, one can use the XCT imaging, which is the middle diagram here, not only to identify the olivine, but really to look at the distribution of these iron, metal, nickel droplets, which again, in these orthogonal projections from the XCT, you can see them located here in this grain. So what we could ideally do is look at the morphology of the olivines, their distribution in the column, and also the distribution of these iron, nickel, cobalt, metal droplets. On the left, we just have, an image showing that these are fairly low in sulfur, the iron metal droplets. And that also illustrates the composition of the iron metal droplets. Once we get to the droplets that actually occur in the pyroclastic glass beads shown up here, the change in iron nickel metal changes dramatically, as you can see here.
30 seconds.
Yeah, okay. And so let me go ahead and show conclusions. The olivine morphology is really important. Based on the occurrence of nickel, iron, nickel metal, there is some indication that maybe this is a product of carbon species oxidizing, forming a reduction of the melt, but we have some other potential method of degassing possibilities involving both hydrogen and sulfur. And this has really serious implications for our interpretation of these volatiles within the melt inclusions.
And
Thank you very much.